So I'm the third in the lineup from London. So I'll be talking about experiments that are sort of underway and being planned. So first off, I wanted to talk about, we heard this great talk by Ephraim this morning on the weak measurements that were done with photons. And the idea here is to really try and replicate these experiments with matter waves. So in our case, an atomic system. And I just wanted to walk you through, once I find the... So basically, there's two slits here. There's this is sort of then, there's a superposition here of horizontal and vertically polarized. There's a weak measurement stage here where there's a phase shift that's imparted that's dependent on the transverse momentum. And then there's an analyzer stage here where you essentially work out what's going on by another projection into the circular basis. And then they observed essentially two interferograms here. So what I want to talk about is really how can we do that. So I should point out that, of course, they were able to make this weak measurement and able to sort of map out this average photon trajectories where they could look at this weak measurement of the transverse momentum of the photon and look at this phase change through the variation in the difference between the intensity of the right and left circularly polarized. Okay, so it's a very nice experiment here with photons. So the question is, how can we do that with an atomic system? So we need to find basically a pointer for atoms. And so for photons, we have this basis of horizontal and vertical polarized. But for atoms, you know, we have something a little different. If we consider really the magnetic sublevels of in our case, a J equals 2 system. So J equal 2 corresponds to metastable argon atoms, which we happen to have in our lab. So this seemed a useful thing. So now the basis state is these M states, which there are 5 of them. So this is kind of going from a birefringent system to a multi-fringent system. And the idea is to sort of base the weak measurement based on phase accumulated by M states as they pass through a magnetic field. So that's the general idea. So this is the type of scheme here. So in our case, we would have a source of relatively coherent atoms, which in our case is cold atoms, laser-cooled argon atoms. We can then spin polarize this, essentially using circularly polarized light and a magnetic field, so polarizing it with respect to a quantization axis. We can then release these atoms, and then they essentially expand and pass through the slits, and then we really want to make a weak measurement here by essentially, so a weak measurement of momentum followed by a strong measurement of position here by actually moving this system throughout the space of where you would expect interference. Okay, so this is exactly the same principle of the experiments with photons. So with cold atoms, of course, interferometry and even as you saw this morning with very complicated molecules. Of course, this has been done. So there's nothing particularly new about that, but what we needed to think about really is how to do these weak measurements. So basically, we need this phase to be dependent on velocity. So what I want to do is just sort of go through these different stages. So the idea here is this first stage, we need to do the spin polarization, which is as I said, in argon, this is metastable argon, which we can laser cool to about 50 microkelvin. And of course, the reason to do that is because it has a fairly large de Broglie wavelength, so it makes, in some ways, the experiment easier. Not if you have to build it from scratch, but since we have that system available, we can do that. And then we use circularly polarized light such that essentially in this, what's called a magneto-optical trap, which holds these atoms, we can then essentially use either sigma plus or sigma minus light, and we can actually pump to one of these states here, so either to the +2 or -2. And so that's our polarization, so it's our kind of like our linearly polarized light, in our case, polarized atoms. And so then then we have just transfer through the slits of these particles. But what we need to really concentrate on then is how we would do this weak measurement. So the first case here is that, so the idea here is that we have basically a magnetic field in this region, okay, and a different magnetic field here, and there's an abrupt change in that field, and such that we essentially rotate that field by 90 degrees, and there's a projection into this, due to essentially a Majorana transition, into a projection of this, or superposition of these magnetic sublevels. So that's represented here, where we come in just one of these states, so the m=2 state, and providing we move through fast enough through this thing so that it's a non-adiabatic transition, then we end up with essentially this type of superposition in these m states. So of course there's also the wave function of the center of mass motion, and I'm just concentrating here on the m states. And so now one thing I haven't pointed out is that so if you just have a region here of uniform field that's changing directions, then you certainly get a phase accumulation in here, which actually I've got that on the next slide. So now I'm talking about actually the center of the magnet here, more magnetic field. So if I just had a straight magnet, then I really get information. So the phase change that I get is information on energy, which actually might be interesting to Basil. But for the moment, we want something that's sensitive to momentum. And this is essentially because if I have particles, that essentially are moving through here with the velocity, the way that I can really determine how their phase is related to momentum is the fact if they're traveling at different angles through here, then they accumulate a different phase. And so we can look at this phase that occurs then on each of these m states, except of course for m=0. And then the next stage is, which is unavoidable, we have another change in magnetic field, and so you would expect to have another Majorana transition. And so you end up, then that phase information is projected into the different m states. And so what I've chosen here for a particular reason is that you kind of have more information than you really need, and perhaps more information than you really like, but that's the way it is with this system that we have. So for the m=0 state, we have this phase information that we can then get by measuring the kind of the probability or the intensity of the number of particles that hit our screen. So then we need to do that, right? So we need to have an analyzer to do this, and there's two ways to do that. One is, so I have all these m states, I can just make a Stern-Gerlach measurement, so I can have a wire with a current through it at the very end of this weak measurement stage and look at these 5 different m states. Or, which is our sort of current preference, is that I can actually just choose to look at, for example, the m=0 state, and look at, and its sort of probability with phase varies in this way. So, unlike the photon system, I mean, the nice thing is if I have a magnetic field, then of course I can change the magnetic field, and so I can change this phase. So, for example, I can take several measurements in the same system with the same distribution of momenta, or weak momentum that we want to measure, and then I can change really the magnet properties. So I can just look at the m states for 2 different magnetic fields. Or I can look at, say, these 5 levels. And experimentally, this is easier because we only need to see 1 interference pattern rather than 5 of them, which might look good, but we figure that might be a bit tricky to do. So that's the idea. So how do we go about doing this, and where are we up to with this? So this is kind of a fairly newish endeavor. So as I said, we have this, what I would call cold, laser-cooled metastable argon source, which was used for other reasons. And So it's at 50 microkelvin, so it has large de Broglie wavelength. And like the system that Rob Flack was talking about, this is kind of nice because it's sitting, not in our case 20 eV above ground, but about 11 eV. And so when this hits a detector like a microchannel plate, then of course you can detect a single atom hitting that. So that's quite a nice system to build up your interference pattern. And so, so this is the chamber that we have. We essentially use gas at room temperature. It goes through a discharge and then a skimmer, and then we we cool it with a Zeeman slower, and then we get this gas here. And at the moment, we're planning to drop the system down through slits. And so this is this long system here. You can see the plasma here and slowing, and then this is the chamber, and we now have this chamber on the end to do the interferometry. And just a few sort of practical things. So we have the slits here, which have been made from molybdenum foil. They have quite large size and quite large separation, which we can do, of course, because we have fairly cold atoms, so we don't need to have such nice slits, although in the end it might be nice to have these slits that are 100 nanometers apart, depending on what we do. And the idea then is we drop this down through a hole here, and we have what we call these are two prisms which enable us to basically drop the cold atoms down through between these two mirrors into the slits, which are in here, which you can't see. But of course, it turns out that we may need to, if we want to make a beam, actually, and we may need to make a beam, because in order for this measurement to be weak, we need to have a fairly small magnetic field, or actually we need this particle moving fairly quickly through the magnetic field. So if we want to change the speed, we have that option. And here is some sort of, this is if we need an extreme speed. So basically we can give this a kick, and you can see part of that beam moving off at a well-defined momentum. So it's cold, but we can actually move it quite fast. So it's important in this weak measurement that unlike photonic or photons, which all travel at the same speed, of course, there's a dispersion that exists in an atomic system. So it's important for us to have, fairly well-defined velocity. And so this is kind of, so polarization, this is the experimental setup. You saw those slits there. We have this weak stage, which is at a slight angle, and then the analyzer here, and we record interference. And so you can see here, this is inside this chamber with this prism, and this is the cold atoms that are sitting sort of somewhat up from here that will drop down through that hole to do the interference. And so, we're at the process where we need, we really need to have this detection system put in, and this is actually an interferogram from Shimazu, I think his name is. They did some experiments on interferometry with neon some time ago, and this is what you would expect. So yeah, there you go, Shimizu from 1996. So the idea here is that we essentially make this weak measurement. And so unlike the photon system, we have to move our weak measurement and our detector together through the system. So it needs to be translated through the system, unlike the photon case where you can use lenses to really move through this plane along the y direction. So in summary, we have this cold atom source. We've got the slits manufactured. We need to construct the weak magnets, and we're awaiting MCP. So thanks for the opportunity to actually talk about something that's not completed, but hopefully by the time of this next meeting that this should be completed. So how much time do I have left? 10 minutes. Oh, fantastic. Okay, so I also wanted to talk about something else here. So this is changing tack a little bit, and also relates to the question that I asked Marcus Arndt, can he keep on doing interferometry to much larger and larger masses? And so I'm preempting a little bit Angelo Bassi's talk here, but I won't say too much. Because what I want to talk about really is an experiment that we would like to do over the next year, but we're sort of close to doing if the funding gods come through, and that is that we would like to look to see whether, to test some of these collapse models. So the idea is that, as Marcus pointed out, there's a number of models, whether it be sort of gravity that induces collapse of the wave function, or that there's some intrinsic noise or decoherence. There's a whole range of models, but there are limits that really extend from mass sizes of 10 to the 7, 10 to 6 AMU up to sort of microgram sizes where you might expect collapse to occur. And so what I just briefly want to talk about is an experiment that really a number of us came up with to use some of the apparatus that we have to perhaps make a measurement on this. And so the idea here is that if you can somehow create a superposition of these sort of macroscopic objects, and I'm talking about something here that's on the size of 100 nanometers, or 10 nanometers perhaps, but certainly 100 nanometers and up. And if this collapse process occurs, then essentially it can appear as noise if you're looking at this system. So the idea is that you get a superposition, it collapses, you get a superposition, it collapses, and so this introduces noise. And so there's been a number of proposals, a lot of proposals recently, notably the one that we were particularly interested in was by Angelo, who will really put this in proper context a little later on, but also Diosi, who is here as well, and another one by Henrik Ulbricht. So a lot of people are thinking about this, but what I want to just quickly talk about is a system that we have that we think is quite promising. And the idea is to take one of these particles, which we actually currently do. We trap these particles. They have a little bit of charge, so we can trap them in a Paul trap, and we can actually then set a laser beam going through to laser cool them to low temperature, in our case, millikelvin temperatures. And you can sort of see this process. If I turn this movie on, it's moving around. It eventually localizes and is cooled down, and in our case, to millikelvin temperatures. So we have this nice cold object that's cycling over. Nice cold object that we can control all the noise that you would expect in this system and hopefully see some additional noise that is due to this collapse process. And so the idea is that we can actually cool with an optical field, and we can turn that off and leave it in this charged particle trap and look for this signatures of collapse. And so I think, I don't know where Dan is. Have you got your poster up now? Yep, so you can really, you can look at this in a lot more detail now with Dan's poster if you have time. And so the idea is that if you put these particles in this trap and there is this noise process going on, then it's a heating process. And you can see that heating process by kind of measuring effectively the number of phonons here, or essentially like the temperature after a period of time. And so these are predictions, if you can hold this particle in the trap for seconds, which we can, how this would change, what the signature would be like, for example, if we looked at how the phonon number changes as a function of pressure. And this is what you would get if you don't have collapse in your model, and these are the parameters for collapse, which Angelo will describe in detail, hopefully. And so you see a difference at very low pressures, and you see a difference for internal temperatures. So essentially, blackbody radiation screws this up if the temperature is too low. So there's noise from that, which dominates, so you can't see it, but at low temperatures you can. If you change the frequency of oscillation, there's also a difference. And also if you change the radius of the particle, and this is sort of critical that the particles we have are right in this range where you should see a significant difference. So if you have any further questions, you should look at Dan's poster, which is there. I should also point out that there was a poster last night for the work on the weak measurements as well. So if you haven't had a look at that, you should take a look. And so just to conclude this last part, so this seems a viable way to test CSL, and we think this is a good system because we can control all the parameters. So this is something we'd like to do over the next few years. Thank you for your attention.